Okay, well, I don't know if other people aren't going to come. So uh, let's, um,
It's just a white bar on the screen.
you only see a white bar.
Yeah, that's all into. I wasn't sure if that was supposed to be there or not.
Oh, no, you're supposed to be able to see the problem.
You got a half an inch white bar across your screen.
What's going on? All right, stop my share. Well, this isn't going to work at all if you guys can't see it. Let me. Well, all right. What I'm going to do is to. How can I do this? All right. First of all, let me try to share it again. You see anything now?
Perfect.
You see it. You do.
Yep.
Okay. Awesome. All right. I don't know. Something like this happened yesterday, and I could never get it to work. So let me, if it does go funny, let me know, and well, I don't know what we'll do. Okay. So so take a second, read the question. And I will, if you don't have the tables there, because not some people's book didn't have refrigerant 22. I will give you tables. But what I want you to do is to think about this problem. This is the same problem we started to talk about at the end of last class. And really what I want to do for today is to work this through in kind of gory detail as a class. So if you if you can, if you actually, why don't you, I know what I'll do. Hold on. In the chat window, I'm going to drop I'm going to try to put in an image, save a copy of this image, and then what I will want you to do is work with a partner to get started on this. If you were there last time, you probably have notes where we got started with it, but the point of this is to get ready to do it on your own. So if you can, try to do it. No, that didn't work. Try to do it by yourself. I'm going to try one more time here. Copy, paste. No, it's not going to go. I don't know if I do this. All right, so yeah. I'm going to upload file. Anyways, so I'm going to upload the file, and the it'll also have the data stuff in the chat window. So it should be coming here as a PDF file here. So it has the appendices, the numbers from the back of the book, and it has the problem written down. Okay, so everyone should, does everyone give me a thumbs up if you see that in the chat window? Does everyone see it? I'm not seeing a.
No, I don't see it either.
You don't see the in the chat window for Zoom. You don't see it.
No. But I mean, it is in the old notes. So
Okay. Yeah, it's there. Okay. All right. So, okay. If you don't see it in the chat window, look in the notes. They're posted on Blackboard. And we're doing the last one, which is a refrigeration cycle. So it's got refrigerant 22. And there are three states in the process. So I'm going to break you up. I'm going to try this breakout room thing. And then I'm going to kind of go back and forth between the groups and then kind of pull it together, and we'll work through the details if people get stuck. Okay. So breakout rooms, we will do put Gabe and Zach in one. And then in the other one, I will put James and Michael. Stefan.
Yes.
I'm going to put you in a breakout room,
Okay.
and you guys are going to work on that problem as a team.
Okay.
All right. Okay. All right. How's it going, guys?
It's going.
Good, are you?
Okay. If you guys have a camera, it might be better so you can bounce ideas off each other and read facial expressions. So do you have the question there available?
Yeah, I took a picture on my phone of it before you changed the screen.
Okay, great. So you have the room, you have the problem. Go through the process. I know, Gabe, you were there last time where we went through the stages. Zach, were you there on Monday? I don't remember.
Yeah.
You were. Okay, great. Don't look at your notes. You kind of already know the answer, but go through the logic of it, because if you can do that, I swear every problem is the same. So first thing to do is to check that you've got, well, you tell me, what was the first thing to do? How do
We
you
made sure each process had two parts of it, so we know we could actually solve for an answer.
each state,
State, yeah.
right? Process is between the states. So don't, right? So yeah, all right, Zach. So that was the first thing was, and I don't mean actually get the numbers so much as just mentally check, oh, is this even possible? Or do I have to do something crazy? All right. So make sure you have two properties known for each state. Then what was the next thing we did, Zach? Right. So the next thing we did was to draw it on a phase diagram to come up with a roadmap. And then we're going to try to pull it all together. And then we have to, then once we know that, then we have to decide what are the values we should be pulling out of the appendices. Okay. So, and then we'll dive into it. Hopefully by then it comes through in the chat window. You should be able to download the files if it ever shows. If it never doesn't show, I'll pull it back as a group and we'll get the numbers. But right now, go through.
Well, I would say, I think when you break into breakout rooms, I think the group chat disappears, so you might have to resend it, but I have that file in the back of my book, so.
Okay. All right.
Yeah.
So, so right now, go through that and verify that it's even solvable. Then draw it, and then come up with a list of numbers that you're going to need from the back of the book. And only then do you actually do it, because these problems are big, and you can waste an hour fiddling with decimal, interpolating, blah 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 blah. You don't want to waste any time. You want to only get the numbers you need. So that means you got to be really clear in your thinking on that. Okay. So I'm going to go get the other group started, and then I'll come back.
Okay.
Okay. All right, guys. So why don't you turn on your videos if you can, and then that way you can read facial expressions and make sure everybody's on top of things. All right. It probably means Michael will have to, he's probably still in his pajamas, I know. Okay. So what's the first thing you have to do when approaching one of these thermodynamics problems? It's like the very first thing.
Can I get the question again? Because when I joined the breakout room, I didn't.
Yeah, sure. Let me, I'll try to drop it into the chat again. We'll see if it goes. Okay, it says to me it's been uploaded. So go to the chat window in Zoom and see if you can get it.
Yeah, I saw it.
Okay, I don't know what happened before, but all right. So the first page is the problem, and then the others are just the properties of the table, the tables. Okay, so when you solve any problem, regardless, what's the first thing you have to do?
See if there's two properties.
Yeah, make sure that you have two properties at each state, right? If you can't come up with two facts about each state, then you won't be able to solve it. So mentally, before you even get into this, go through and check that you've got two properties known for every state. Then make a diagram. Okay, map it out. And so map it out, and then after you do that, you can, what I want you to do is come up with a list of the numbers that you're going to want to get from the back of the book. Okay, and you should do all that before you actually dive into things, right? Because I saw in the other group, you can blow an hour doing stupid interpolations of this and that, and there's so many numbers you can pull out. Most of it is not helpful, so you want to make sure you're doing useful work. So have a plan. It's really important to have a plan. I think you guys can use the whiteboard feature. Can you try that? See if that's an option for you guys. You go to share screen. Do you guys have that option?
Yeah.
Okay. I'm going to do multiple participants can share simultaneously. Okay.
Yeah, it says one of the hosts can share on this meeting.
How about right now? I just changed it.
Oh yeah.
Same?
No, you can. It gives you a plethora of options.
Okay. So now you should, so if I stop my share, okay. So now you guys could use the whiteboard feature to map it out. Okay. All right. So I'm going to go back to the other group. I'll be back in a minute. So I want you to go through, verify that you've got enough properties at each state, construct the diagram, go through the logic of that, and well, then I'll be back by then. Okay.
Well, do we need just a PV diagram, or do you want a TV diagram as well?
Both. The problem tells you to make both,
Okay.
but qualitatively, the phase diagram part qualitatively is the same. Now, the way an isobar and an isotherm is going to look different, though.
Mm-hmm.
So, yeah.
Okay. Yep.
All right. So I will be back.
I was just gonna say, I don't know if I was there, because some stuff he talks about, sometimes I think that might have been when I thought it was just come in for help. So there was a couple classes the 1 week, I didn't know they were class, I guess, but yeah, so that would be refrigeration.
Did you, hold on, you can you can use the whiteboard feature and you can draw in Zoom. So you can share your ideas too. So I think you can try that. If you go to share screen, one of you guys, does it give you an option to share a whiteboard?
Yeah, whiteboard's there.
Go ahead and try that, and then let's make sure it kind of works the way. Awesome. Yeah, so I can see that. Let me see if I can draw on it.
Let's see, how do your screen sharing? Can you take over my screen?
I don't know. That's what I'm gonna see. I'm not seeing that option here. So, okay, you guys would have to have your own, maybe go back and forth, I guess.
Yeah. Well, I know back last semester when we were doing programming, you would take over my screen and like literally type over on it.
Right.
Yeah. That's, I guess you can't do that with a whiteboard.
Yeah.
Yeah, I don't know. So we know it's a refrigeration cycle. You can also look at like process 2 to 3, you're losing work. And the next one's adiabatic, which means there's no heat loss. So that kind of
Okay.
That mean,
there.
would the pressure go back to the original pressure then, or
Which one?
from step 3 to back to step 1 for adiabatic expansion? What would change there?
Well, so if you go back, what you know is that it's because it's a cycle and you're back at state 1, the pressure the final pressure is back to where it started. What you really know when it's adiabatic is you just know that the heat is 0. Adiabatic doesn't necessarily mean anything is constant. It just means there's no heat.
Okay.
Okay, so run through with me. State 1, do you have two properties that you know?
Yeah.
What do you know there?
It's constant pressure. The first pressure is 30 psi and the quality is 0.95.
Awesome. Where does that put it in a phase diagram?
That's closer to the saturated vapor side of
But
the
it's
curve.
inside the
Still
little
inside the curve, yeah.
saturation curve. Good. All right. Zach, state 2. Do you have two properties for state 2?
It jumps up to 40 degrees Fahrenheit and what else? I'm not really sure.
Look at the process that connects 1 to 2.
Constant pressure. So the pressure is going to be the same.
Pressure's the same. So now you got 2 numbers there, right?
So are we using on that table that a negative 11.82 that corresponds to the 30 pounds?
Hold on. There's no table yet. We do all your planning with no table, right? Yeah. Because you can get lost in the table. Have a plan, right? Go work it through mentally and get a list. I mean, when I worked it out, I can show you. I don't know if you can see this. So when I worked it out, first thing I did at the bottom is my list of numbers that I want to pull out of the table without even looking at the numbers. Okay. Okay, so you got two properties there. Gabe, what about state 3? You have 2 numbers there.
It's constant pressure going to 3. So temperature is still going to be 40 degrees, right? Fahrenheit.
Hold on, you told me from 2 to 3, the pressure's constant. Is that right?
I mean, sorry, temperature. I'm slow.
Temperature is constant. So you know the temperature. That's one number. What else do you have?
Oh, it's at the saturated vapor.
It's in the saturated vapor.
Next is 1.
Right. So quality is 1. Yeah. So so now you verified 2 numbers for everything. Okay. All right. Now I want you guys try to use the screen share and try to map it out. Try to draw it draw a PV and a TV diagram. Okay.
Right.
All right. See if you can figure that out. And I'm going to go to the other group and make sure they're. What's that?
I was gonna ask Gabe if he has a touch screen that he could write on, because I don't, so it might be better.
I'm gonna use a mouse and dink with it.
Oh,
so.
Okay.
All right.
I'll get it.
All right. So I'm going to go to the other group and see how they're doing.
All right. Sounds good.
Minus Q, Q minus work, which is Q is 0 because it's
And we-
static. I think we can just look up the internal energies.
Oh, you mean from like, so whatever the heat was at, would it be the heat or the pressure? How would you look that up?
Um,
Well, okay, fine. Do you have to? Although, I mean, looking at the diagram he drew, the PV diagram he drew, 1 to 3 is a straight line, so there would be no work under it anyway.
oh, all right.
Yeah. But how would we know that? Like is there
Mason, I
anything
don't
we could?
think I may have drawn it badly. It wasn't.
Oh, really?
It really isn't.
You're here.
So before in the last class,
Mhm.
before that, we worked out what an adiabat looked like for an ideal gas.
Oh, okay.
And this is not an ideal gas, right? It's in the mixed state. It's, but
Right.
what we just worked out is that it tends to be a little bit steeper than an isotherm kind of thing. So it's just sort of a steeper diagonal curve. So really all I did was I knew that state 3 was saturated at a higher temperature and pressure. And I knew that state 1 was a little bit inside the saturation curve because the quality wasn't quite 1.
Okay.
And so I just connected them up with with some sort of curve there, just sketched it in. So it wasn't meant to be it's not isochoric. So
Okay.
what do you know about the process from 3 to 1?
It's a. How do you say that word again? I don't want to mess it up.
Well, we all love to hear you say it. Adiabat.
Adiabatic. Okay.
Yeah, it's an adiabat or it's adiabatic. And that means no heat.
Right.
So Q from 3 to 1 is just 0.
Mm-hmm.
If Q from 3 to 1 is 0, how can you find the work from 3 to 1? And you don't know the curve, you don't know the formula. Like it's not something you can't do that integral.
Right. I mean, well, we know that the work must be equal to the change of internal energy. We
You
know
got it.
that.
You got it. Up to a minus sign. Yeah.
So does that mean we're looking tables up or values up in the table?
Yep. So when you look up the U values, you subtract them. That's going to give you the work.
And we're doing that for the pressure or the temperature because we really don't. We have.
Well, it doesn't matter. You went through. You've got you got two properties for state 3. You can get its internal energy. You've got two properties for state 1. That's enough to get its internal energy. You have to look it up in the table and stuff, but that's it. Once you get those numbers, it doesn't matter which graph you look at. You've got the state 1 and state 3. You've got the numbers. Just subtract them. Okay.
Mm-hmm.
So do we have a list of numbers that we need to pull out?
Well, let's
Oh,
see.
boy.
We're gonna need a couple of things from the table actually.
Need V2
Why do you need V2?
to find the work from 1 to 2.
And it's like what you have there. That will work. You know the pressure, and you can do delta V. The other way is because it is an isobar. The heat for an isobar is delta H. So you could look up delta H and delta U and find the work from those.
Wait, how do we know it's an isobar? That's not given.
1 to 2 is isobaric, right?
Oh, constant pressure from P1.
Yeah.
2. Okay.
So, and because it's isobaric, you can say that the heat equals the change in enthalpy, only true for isobars. And then you can go through the first law to say that the work is the change in enthalpy minus the change in internal energy. And those numbers could be looked up. Michael, the reason I might recommend doing that is because for the other, I think the other numbers you're going to need are internal energies and enthalpies and stuff. So if you can phrase it all in terms of internal energies and enthalpies, it might be one less number to pull out. I don't know. You know, there's not always one way to do this stuff, but
So work equals a change in enthalpy minus change in internal energy.
yes, for an isobar, only for an isobar. Because for an isobar, I'm saying, so really I would be saying work equals Q minus delta U, just
Mhm.
right? But for an isobaric process, Q is delta H. That's all I'm saying. You can do it either way, you'll get the same answer. All right. Sapon, you doing
Yeah.
okay?
Yes.
Okay, all right, I couldn't see any. All right, so are you guys in agreement? Do you coming up with a plan for what numbers to pull out?
Hmm?
Yeah.
More or
Were
less,
you-
I guess.
Were you able to get the phase diagram? Did you draw that and did you were you able to construct that on your own?
I think we were more focused on trying to figure out the work rather than draw the diagram.
Do the diagram. For this one, it's not, I mean, maybe not so crucial, but for other problems that will be really useful. So make sure you can draw the diagram. Okay. All right. Keep pushing ahead. I will, I'm going to go to the other group. You guys are making progress. So just keep going around that cycle, work your way around the loop and come up with a plan for each heat and work number, how you're going to evaluate it. And
So
then
what did you say work was equal to for an isobar?
for an isobar, so what Michael wrote there is true.
Mm-hmm.
It's P delta V. That's one way to do it. The other way is you can use the first law to say that the work is heat minus internal energy. Q minus delta U. And then for an isobar, Q is equal to delta H. So up there at the top of the white,
So be loud.
up there at the top of the whiteboard that Michael put, he wrote work equals delta H minus delta U. Can you see that?
Yeah.
Right?
Yeah.
That's true only for an isobar. So these two formulas he has, they're just two ways to get it. You'll get the same number.
Okay.
Yep. Okay. I'm going to go to the other group, see how they're doing. Keep pushing. Get a list of all the numbers you want to pull out.
I was just reading that off the problem.
Okay. Somebody. All right. Somebody.
I drew it once and my thing lagged out and it deleted my whiteboard. So I just plugged my iPad in.
That's fine. Welcome to my world. That happens.
Mm-hmm. Literally just finished drawing it and it just deleted it. So
It really sucks when you made a 45-minute video explaining something and the whole thing craps out on you.
oh, that
Okay.
annoyed me.
Zach, explain to me how where these diagrams came from.
Well, I mean, you know the curves for both of them, and you just have to move stuff along, whether temperature's constant or pressure.
Tell me how. So state one is placed at some point, right? Someplace. How
Yeah,
do we know-
0.95 on the saturated. Quality is 0.95, so it's under the curve, and it's closer to the saturated vapor side.
Right. So that's how you know. Quality tells you there. Okay. And then state two. So if I look at the PV diagram, state two, how did I know where to put that? In the PV diagram.
You have constant pressure, so you just make a straight line over, because if you didn't, pressure would be changing. So.
Yep. Awesome. It's that simple. All right. What about the TV diagram?
Yeah, that one you got to follow the isotherm.
Yeah.
anchor.
And and it's a little tricky here. It should be when you're inside the saturation curve, the isotherm is horizontal. And then once you leave the saturation curve, it becomes, it kind of kicks upwards, like it goes up on the diagonal. All right.
Okay.
And then how do you go from 2? Yeah, that's kind of, yeah. Yeah. And then from 2 to 3, how do you go from 2 to 3?
Constant temperature means
Yep.
horizontal line.
And you finish on the saturation curve. Yep, you got it. And then, yep. And then he drew in there an isotherm. It's roughly like he did up there in the top graph on the PV diagram. Yeah, awesome. And then you just close it all up. Good.
Going for 3 to 1, you just have to connect the dots, basically, right?
That's it. Yeah. I mean,
I was wondering like why it was almost straight down. I was just
I
curious.
think I made my diagram really squeezed, and so it just looked that way.
Gotcha.
Yep.
What was I gonna say? Yeah, that's not too bad. I think the hardest part is just making sure you look at like each process, and there's even though like you go to the next process, there's still words in the last one that hint at what the next one will be.
Yep. And that's very, very common. That's how
Okay.
it will usually be. Yep.
Let's just analyze.
Yep. Yep. It doesn't give it to you all in like one nice place. You kind of have to read through it and there's a bit of a dance that you do. Okay. Awesome. So how are you going to get your numbers?
Book.
Yeah. All right. What numbers do you need to pull out of this thing?
Well, I know we're probably gonna need the specific volumes.
Well, hold on. What's the goal?
We got to find the heat, the work, and we already did the graphs.
So so think about from like 1 to 2, how could you find the heat or the work?
From your calendar.
Sorry.
Sign.
Going 1 to 2. Well, you know it's going into the vapor phase, so you're gonna be looking at the either the pressure table, the liquid vapor, but you're on the far right side.
Well, what do you know about from 1 to 2?
Pressure is constant.
Do you know how to evaluate work when pressure is constant?
Yeah, we wrote it down. When it's iso what is it?
Well, you know the formula for work, right?
Change in enthalpy, right?
Huh?
Change in enthalpy.
You can write it that way. There is a way to write it that way, or you could say it's pressure times delta V. That would work too.
Pressure times.
You can also write it as so right. Yeah. Why don't you write that, Gabe, right there? So from 1 to 2, you could write. So write that. Yeah. P equals delta V. Sorry. Work is P times delta V. Sorry. Because pressure is constant and it pulls out of the work integral. The other way to say it is from the first law. You'd say, well, the first law says heat minus work is delta U. Therefore, work is heat minus delta U.
Yeah.
All right. So why don't you write that down? So you do, or there's an alternate way. It's the other way. Q minus delta U. Okay. And then for what is the heat for an isobaric process?
What is the heat?
For an isobaric process?
That's change in enthalpy, right?
Yes. So you could say then work is delta H minus delta U.
Work is delta H minus delta U.
Yeah. Right. So that's how you can do it using.
Okay, I see what you did. You plugged in. Okay.
Okay. So either way will go. That will work. Okay. All right. So that means, I mean, I would probably recommend pulling out enthalpy and internal energy numbers, but that's,
Yeah, that would make sense.
okay. So you get those numbers. So that would mean you need H1, U1, H2, U2, right?
Mhm.
Um, Okay, how do you go from 2 to 3?
Let me read here again. 2 to 3, constant temperature, saturated vapor. Well, they already give you work. So for that part anyways. So we don't have to find that. We just have to find heat.
Okay,
Um,
yep. Is there any, it's kind of an isothermal thing, but it's,
yeah, that's constant temperature. So
but we don't really have anything special going, like there's no general way to do that. So you're gonna have to use the first law. So
All
how do
right.
you, what is the heat equal to then? Heat equals, okay, yeah. So, and you know the work from 2 to 3.
we can find we can find the internal energies, right?
Okay, so now add that to your list of numbers. So you need H1, U1, H2, U2. So let's, but don't, delta U isn't in the table. Let's just make a list of numbers that you want to pull out. You want to pull
All right.
out H1,
W2.
U1, yeah, U3. You'll want delta U there from 2 to 3. And you'll want H1, H2. Okay. Now to go from 3 back to 1, how do you do that?
Let's see here.
How do you do
Well,
that?
it's what is it? Adiabatic, right?
So what does
So
that
that
mean?
means Q is 0. Heat
Q
is 0.
So what is the work equal to?
Change in internal energy equals negative work.
Okay, but at this point, you already know U3 and U1. If you've done all
So
these numbers.
signs after you find it, right?
Yeah, so you just, once you get all these other numbers, you just subtract them and you get your answer.
Yeah.
Okay, Zach, you haven't said anything for a bit. Are you doing okay?
Yeah.
All right. You see how we're kind of feeling our way through this, come up with a laundry list, or a grocery list is a better word for it, of numbers that we're going to go through and pull out.
Yeah.
And if we can, I don't want to do any extra work numbers, right? Because that takes forever. It just does.
What kind of conversions? Do you need any conversions between whatever the standard for to BTUs or whatever?
Well, that's okay. So that I was going to come back to that. That's one. So I kind of steered you. How did I steer you for finding the work from 1 to 2?
Pressure.
Good, right, is P delta V. But what did I suggest?
The first law.
Yeah.
Start at the first law and work your way back.
And the reason I did that are the unit conversions. Because if you do it with enthalpies and internal energies, it just automatically comes out in BTUs per pound mass. If you do it with PV, then you have to use that 778 conversion factor and you got to worry about it.
So in all honesty, we don't have to use this one. We can use this one.
I would use that one. And then the unit conversion is just done for you.
Because the first one to me, like, I don't think I would have thought of that on my own.
Okay.
The second one I would have thought of.
Okay. I mean,
So, don't want to write something down.
Yeah.
I'm not confused.
so Zach, does that answer your question?
Yeah.
Yeah. If you do it with P delta V, it will come out in like foot pounds of energy. And then you got to convert it to BTUs. But if you do it with enthalpies, it's already tabulated in BTUs. You're just good to go. All right. I'm going to.
When were you
Go ahead.
thinking of having the next test? When do you think that might be?
I think we're going to do it on Wednesday, but I'll tell the whole group as a whole. I think on Wednesday. Yep.
This
Yeah.
coming Wednesday here?
Yep. In class. So, do you guys have the tables? Did I get that to you guys? I was able to drop it into the other group.
PDF, yeah.
You were or were not?
Yeah, I have it.
You have the files, the data files for the lookup
Yeah.
stuff? Zach,
Yep.
do you have that too?
We had it in the main group chat. I don't have it now, but is the stuff in the, I think the
It's in your
stuff's in my
book.
book. If we're,
It's in your book. Yeah, I think your book's
Yeah.
different than mine. So,
Both
yeah.
of our
mine-
books have it.
Somebody had a book. Somebody's version didn't have R22. That's the reason I was.
Was it Alex? I think it
don't
was
remember.
Alex. It was
Oh.
him or the books that Paul was using.
Okay. Okay. So, all right. So everybody should have that. Okay. You know what numbers to get. Go get them.
Sounds good.
Looking up a bunch of different enthalpies and. Okay.
All right. So do we have a list of numbers we need?
Sort of. We're
Okay.
closer than we used to be.
Okay. Go ahead. Tell me what you're thinking.
All right. Go ahead, Mike.
Using the quality, we can find U1 and H1.
Good.
Then we can find H2, U2 from the tables.
Good.
And then we already know the work from state 2 to 3. And then from state 3 to 1, we just need to change, just need U3. Then we
Yes.
just subtract that from U1.
Okay. Sounds like you got it. I meant to, there's something I forgot to say, because you had said also you could use work as P delta V. And I forgot to say why I steered you towards using enthalpy. If you do P delta V, what units will that come out in naturally?
BTU.
No, it'll come out in foot pounds when you just do it. And so then you
Oh,
have to convert it to BTUs, which is that 778 number. But if you do it using enthalpies and internal energy, it's already tabulated in BTUs.
In BTUs.
So that I couldn't remember why I did this the other day. And I couldn't remember why I decided to steer everyone towards that way. It does just shortcut one step.
So wherever possible, use enthalpies and internal energies
I think
before.
it just, yeah, I think I would. It just, because you have to do the pressure. It'll come out in PSI. You have to convert that to PSF. So that's a factor of 144. And then you have to use this 778 number somewhere in there. Yeah. I mean, it's not like it's hard. It's just stupid work. Whereas if you use enthalpies, it's done for you. Okay. All right. You got your list of numbers.
we're stuck on trying to find the internal energy for 3.
Internal energy for 3. You know it's saturated liquid, or sorry, saturated vapor, and you know the temperature, right?
Mm-hmm.
So, okay, let me look up.
But would we need no pressure?
Well, because it's saturated, if you know the temperature, you'll automatically know the pressure as well. But I would go to, if you've got those tables, I would go to the saturated. So hold on here. Do you know? I can't remember here. I got a question. All right, hold on, guys. Just one second. I'll be right back. So, somebody's at the door here. Sorry, I just have to. Hold on. Oh, it's the wrong. Struggling with this here. Oh, there it is.
Yeah, I think we're almost ready.
Awesome. All right, so I'm gonna go check on the other group. They're doing well too, so we'll pull it all together.
All right, so we know, did you find?
I think this one would be exactly the 94.86. Zach, right? Because it's at the saturated vapor stage. So we have to multiply it by
yeah,
nothing. Yeah.
right.
This will just be 94.86. Sean, for U1 and H1, saying we're at a quality of 0.9 whatever, do we just multiply that by that value and that will be our actual internal energy and enthalpy?
Well, you use the formula. It's going to come out very close to that.
I
But
figured.
you're going to say it's 0.95 times U saturated vapor plus 1 minus 0.95 times U saturated liquid. Because remember the liquid part,
What's that name of that process? Or was that interpolating?
no, but we did it all in about the same day or two. So
Yeah, because like I don't really know what interpolate, like the actual formula of that is. Because
it's just using quality to find properties.
Okay, gotcha. All right, so you said it would be 0.95 minus something? What was it?
So the formula is U equals X times U saturated vapor plus 1 minus X times U saturated liquid. Mhm. And the idea is it's, the part that's vapor, well, it's that fraction times the saturated vapor number. And then the fraction that's not saturated vapor, it's used liquid.
Gotcha. I see what you're doing. Okay. I think besides that, we have all the values we need. Double check here. Now, is that process the exact same for the enthalpy also?
Yeah, same for enthalpy and same for entropy when we get there.
Entropy also. Okay. All right, Zach. So I think all we have to do now is just plug and play. So I'm gonna scroll
Yeah.
down here. Zoom out.
Are you gonna pull us all back, Sean, or you're muted?
I was saying bad things about you guys. The other group's right about where you are. So just push through a little bit more and then we should all be able to compare.
Gotcha. Oh, we didn't get U saturated vapor. Okay, so we only have U saturated gas. We need to find the liquid.
At 30 saturated liquid, 7.44. At 30.
At 30 pressure,
Yeah.
I got 7.38.
Well, I mean, on the table, the saturated liquid, it says 7.44. Does it say 7.38 in your table, or?
Yeah.
Oh, okay, whatever. I
Table
don't-
A8.
That's not going to matter. That's just, they have to define a 0 point because it's all measured relative to something. And between the additions, they sometimes shift them.
Gotcha.
But the changes in U will always be the same from book to book.
All right, so now we have everything we need. Okay, so back down here, sub vapors, this would be a 93.67 plus.
All right. I'm going to give people a couple minutes and we're going to pull back to the main group. Okay. Keep working.
Sounds good. This is just U1. This isn't even changing U, is it? I just thought about that. Okay. So Zach, did you get 89.36?
That sounds right. Yeah.
All right, so I'm gonna do the same thing now for H. All right, so got 98.55.
Oh, oops.
Mars might be a little different. Well, unless you use the
But when you
7.4.
compute the changes, it'll come out the same.
Okay.
So if that's
Well,
right-
in between the 0.95 and the 103, I hit plus instead of times, so I got a different number. So gotta
well,
do it again.
then you got problems. So probably, Zach, all of your U's and all of your H's will be different by that same amount, so that when you subtract numbers, it cancels. But I'm guessing that's what's going to happen. All right. So you have U1, H1, then you get U2,
It was I'm sorry, U2
H2.
was 1.4.
I think that's on the table, right?
Yeah, it was.
Okay. All right. See you on the other side.
Sounds good.
All right.
Okay, so how do we feel? Do we feel like we kind of understand how to pull this together? So you guys are on the same, work in the same direction. So I'll just quickly summarize here before people have to go. So what we found, let's see here, the heat from 1 to 2, you could just write that as delta. That's the specific amount of heat, would be delta H1, 2. The work from 1 to 2 would then be the heat from 1 to 2, delta H1, 2, minus delta U1, 2. The work from 2 to 3 was given,
Mhm.
and therefore the heat from 2 to 3 would be delta U 2, 3 plus the work from 2 to 3. Is everybody okay with that? So all this so far?
Mhm.
And then the heat from 3 to 1 was 0, meaning that the work from 3 to 1 would be just delta U 3, 1. So that would be 1 minus 3, because it's from 3 to 1. From 3 to 1. All right, so that means I need to look up numbers H1, H2 for this bit, and I need U, sorry, U1, U2 to get this number, and then I'm going to need U3. Okay? So these are the numbers we have to pull out. I think both you guys, both groups had the same list of numbers. Yes? I think so. Now,
Good.
the hardest one to handle, I think, is going to be state 1 because you have to use the quality formula. So for U1, you're going to use the quality formula. So that's going to say the quality times U saturated vapor plus 1 minus quality times U saturated liquid. And this is all at, you want to use 30 PSI. I hadn't, with the first group, I didn't check. Is this how you guys went about doing it? Did you use quality like that? To find the internal energy? Okay.
Well, I don't know who group 1 and group 2 are.
Oh, sorry, the 3-person group. Mason.
Yeah. We started solving for U1 and U2, or U1 and H1.
Okay, so, and then H1 is going to be the same way. X.
Right.
U, sorry, I keep writing. H saturated vapor plus 1 minus X. H saturated liquid. Now, because the quality is so close to 1, you know the answer is going to be pretty much the saturated vapor numbers. A little bit different, but close. So what did you guys get for U1?
U1, I got 89.3555.
Okay, 5, 6. Okay, that's BTUs per LBM. Does everyone get the same number there for U1? Zach, you had a different number though, right?
When I ran Gabe's numbers, that's what my number in my table for the one thing was like a couple hundreds off. But.
Yeah. So Zach has a different edition of the book, and all of his U values and H values are shifted by a constant amount. So that can happen, but when you compute changes in energy, the constants cancel and you get the same change. Right? H1 is what? That was 98 something?
98.55.
Okay. What about, and then for U2 and H2, those are just in the table. You can look them up. So what were those numbers?
U2 was 100.40.
100.40?
Yeah. And H2 was 111.43.
111.43. Now notice these are all intensive quantities per pound mass. Okay. And the issue is they didn't give us the specific amount of work. They gave us the total work, I think. Yeah. So to be able to mix it in this formula, I actually need to divide by the mass, which fortunately is 1. So it's okay. But you just, in another problem, you got to watch that. Okay. The different numerical difference between the intensive.
Would you divide the work or all your other values?
Doesn't matter. But since
way.
all the other math we're doing is with the intensive thing, I probably would just convert the extensive work into an intensive work, do the arithmetic, and at the very last step, convert everything out. But okay, yeah. Doesn't matter. You end up the same place. Okay. And then for the last numbers, then I'm going to need U3. So how do we get that?
U3 is 94.86.
4.86. How did you get that?
I looked it up.
And it's on the saturation curve, right?
Yes.
And you knew the temperature for that one, if I remember right.
Temperature is 40. Yeah.
So you're going to use the temperature page to get that, whereas you used the pressure page earlier. So you got to flip between them. Yep. Awesome. So you got all the numbers. All right. So we've got all 3 internal energies. We needed the 2 enthalpies. Got them. And then this is how we work it out. You're going to do H12. All right. You subtract them all out. Did anyone go through it all and get the final numbers here?
Yeah, I did.
Okay. So what did you get?
The work for 1 to 2, I got 1.84 BTU. Yeah.
Yeah.
For Q, I got 12.88. For 2 to 3, you know the work. For heat, I got negative 6.28.
Give me 1 second here. I need to write it down. It was, I had it written down. Negative 11.82. Use. And then the heat from 2 to 3, what did you
I
get?
got negative 6.28.
Okay. And
For
go
3
ahead.
to 1, heat is 0. And for work, I got 5.5.
Okay, now hold on here.
Check me
This
if I'm
is a
wrong.
refrigeration cycle. So we expect the heat to be negative. And we expect the work to be negative. And I know it's a refrigeration cycle because of the diagram, right? You went, basically you kind of go this way, this way, this way. So you're working clockwise, sorry, counterclockwise. So it's a refrigeration cycle. So we got to be careful. Did we get, when we did these delta U's, did you do final minus initial or did you reverse it?
For the first one, 1 to 2, I did 100.4 minus 89.36.
Hold on. I got to go slower. So you're doing Q1, 2. So you're going to do H2 minus H1.
Yeah,
So it's going to be 100.4 minus, sorry, no, it should be 111.4
yeah.
minus 98.
I'll do it again real quick, just to double check that answer. 5.5, that's for the change in enthalpy. Then for the internal energy, I did 100.4 minus 89.36.
100.4 minus 89.36. Okay, that seems right.
And I got negative 98.16. What did I do different this time? Hold on.
Negative 98.16. That's delta U. No, that's U. Was it?
No, that was for work. Work is change in enthalpy minus
Okay, so
change
that's
in
the
internal energy.
total result you're getting. Okay,
I also did that one wrong.
hold on.
All right, disregard these answers then. 'cause I'm
Yeah,
gonna
we got to get
again.
the. All right. We're kind of running out of time here. Let's go through. Does everybody have the same numbers for H1, U1, H2, U2, and U3? Are those numbers matching? If those numbers are matching, let's just work it all out right here. Okay. So I'm going to have Q12, which is delta H12. So that's going to be H2 minus H1. Call out those numbers. What was H2 and what was H1? Let's see here. So for H2, I'm getting 111.4. Minus H1, which is somewhere 98.5. So that's looking like that's going to be 12, 13? No, 13. No, 13. So I'm getting about 13 BTUs there. Is that what you have? Then the work from 1 to 2 is going to be delta H12 minus delta U12. So that's going to be about 13 minus, and it's going to be U2 minus U1. So that's going to be 100.4 minus 89.4. 100.4 minus 89.4 is 11. So that's about 2 BTUs, the work from 1 to 2. You guys get the same number there. In round numbers, I'm doing it in my head here. And that makes sense that it would be that way because when you go from 1 to 2, it's an expansion. So the work should be positive in a PV diagram because it's an expansion from 1 to 2. All right, the work from 2 to 3 was negative 11 point, is that 5.2 or 8.2? I can't remember. I think it's 8.2. My notes are scribbled here. I can look up here. 8.2 is the number. BTUs. And then the heat from 2 to 3 is going to be the work from 2 to 3 plus delta U from 2 to 3. So that's going to be negative 11.82 plus, it's going to be U3 minus U2. So go back to my numbers here. Oh, that's going to be 94.8, 94.9. Let's just call it 95. And U2 is 100.4. So it's 94, 95 minus 100.4-ish. So I'm getting about, it's going to be like 5.5 roughly. Negative 5.5. So this is about negative 5.5. Pulling it together, this comes out about negative 16, 17 plus change. Okay. Does anybody have a better number? More, you got the calculators there. What do you have for Q23? Nobody wants to say. It's okay. All right. Q31 is 0, and therefore the work from 3.1 is U3 minus U1, delta U, and that's going to be 94, 95 was U3, and U1 was down here 98.5, so that's going to be 98.5 minus 95. So that's going to be 3.5 approximately. Okay, so now I can add them all up. The work for the cycle would be 3.5 minus 11.82 came from the problem. Plus 2. So I'm getting a work of, 11.82. If I have 5.5, so that's going to be 6.3. Am I doing it right? I don't know. But anyways, it's negative 6 something. So the work is negative, and it's going to add all up. All right. And then the heat, now I've estimated so many times, I can't say it with certainty, but in round numbers, it should be pretty close to negative 6 if I've done this right. And I get 0, I get negative 17 plus 13. Okay, so it's coming out to be negative 4. I think it's just rounding issues. It's about the same. So that's going to work out. Okay, I'm sorry it's kind of a muddle here at the end. But watch your minus sign. So Gabe, what I think probably happened was that on some of your delta U's, you might have
flipped them. Yeah, I did.
Flipped them. And so the heat, so from 1 to 2, that means 2 is the final one.
Yeah.
I
don't know why I did that. I knew it after I looked at it, but
it's okay.
Now for 3 to 1, I got a work of 5.5, and that's subtracting 94.86 minus 89.36.
Oh, maybe I think I just double rounded it in my head and whatever.
Okay, I just wanted to make sure I didn't like my.
So
calculator
you're getting
didn't
from
dumb.
the work from 3 to 1, what are you getting?
I got 5.5.
5.5,
Yeah.
which is going to make this number, that's better. That makes the two numbers match a lot better.
Okay.
Yep, that's moving in a good
From your
way.
calendar.
Yeah.
Social studies Kautzman.
Sorry.
Starts in
Everything
2
else worked out roughly the same. So
Our house Alexa rules the schedule. She tells classes.
From your calendar. Social studies Kautzman. Starts in 2 minutes.
So my middle schooler knows when to start. Yep. So that changes this to about a 4.3. And that's what I was getting. -4 was about the heat. So that's about right. Okay. Whew.